as a group, taking our time. Okay, Chemistry 1411. We're in chapter 16 now. You've already written 3 exams in this class, and your next exam is going to cover this chapter, chapter 16, which is thermodynamics, and also chapter 17 in our textbook, which deals with electrochemistry. Well, let's get started in our adventure in thermodynamics by talking about spontaneity. Right? You guys all know what spontaneous means, right? It means a process that's going to occur without outside intervention. For example, if I roll a ball down a hill, that ball is going to spontaneously, or if I push a ball down a hill, that ball is spontaneously just going to roll down that hill. I'm not going to have to intervene at all. The ball is just going to keep rolling down the hill, right? It's a spontaneous process. It's occurring without outside intervention. What if I have a hot cup of tea, right? Here's a nice hot cup of tea. Well, I know that the heat from that cup of tea is going to flow from the cup of tea outside, right? The heat is going to leave the cup of tea, and that cup of tea is going to cool to room temperature. And so that heat flow from the cup of tea to the environment outside of the cup of tea is a spontaneous process. It's occurring without any outside intervention. Just as an aside, something that you want to note about the flow of heat, and this is true 100% of the time, that heat is always going to flow from a hot body to a cold body, right? It's something that we know in our everyday life, but now you've seen it in chemistry class, so it must be true that heat is always going to flow from a hot body to a cold body. Again, 2 spontaneous processes. They both occur without anybody intervening from the outside. Well, what if we take a look at this concept of spontaneity from the point of view of chemistry? And what if we were to take some magnesium, just some solid magnesium, and put it in sulfuric acid? Well, that's what's happening here, is that somebody mixed some magnesium, which is a solid, plus some sulfuric acid, which is an aqueous solution, and they end up producing magnesium sulfate in the solution. And you can see some, can't tell if that's really vapor coming out of here, but they also produce some magnesium sulfate and some hydrogen gas. Now, this is a spontaneous reaction. You don't even have to try it. Take it my word for it. If you just take magnesium metal and you mix it in sulfuric acid at room temperature, 1 atmosphere of pressure, you're going to form magnesium sulfate and hydrogen. But what you're not going to see happening is that you're not going to get hydrogen and magnesium sulfate combining to reform magnesium and sulfuric acid. It's not going to happen, okay? So here's a spontaneous process. In this case, it's a reaction. So this is a reaction that's spontaneous because it's occurring without any outside intervention. We just mix the 2 starting materials together and we end up with the reaction like that. And you guys could probably come up with other examples, without my help at all. Here's a very common example of a spontaneous reaction. We don't see this reaction as much in Colorado since the climate here is so dry, but I was born and raised in Nova Scotia, and I can tell you that there's a lot of rusty cars in a place like Nova Scotia, which is right on the coast of the Atlantic Ocean. In fact, you can't escape the Atlantic Ocean when you're in Nova Scotia. So we see that the iron in an automobile panel, let's say, or the rocker panel, it's going to combine with oxygen and water, and it's going to form rust. If you're wondering what rust is, it's basically iron 3 oxide, and it's probably a hydrate, like a trihydrate or a monohydrate or something like that. That's a spontaneous process. Okay, again, a chemical reaction that's a spontaneous process. But you're never going to take your rusty car and just turn around one day and all of a sudden the rust has disappeared and it's gone back to being, back to its original state. That's a non-spontaneous reaction. And so to summarize what we've seen on these first 3 slides, a process that does occur naturally under a specific set of conditions is called a spontaneous one. That's a spontaneous process. And a non-spontaneous process is going to be one that doesn't occur naturally under some specified set of conditions. Now, the reactions that we've been talking about so far have all been at, atmospheric pressure and probably room temperature. But there we go. Now we've defined what a spontaneous process is and a non-spontaneous process is. Now, I remember learning this when I was in high school chemistry. I took, advanced high school chemistry and talked about spontaneous and non-spontaneous processes. And I remember thinking, like, the first connection that I made in my mind, and I wasn't right, but the first connection I thought, hey, spontaneous reactions, those must be quick reactions, things that occur really quickly, like an explosion. Well, you don't want to mix those two concepts up, okay? Don't mix up the concept of spontaneous with fast. These are two different things. A spontaneous reaction, hey, a spontaneous reaction might be fast. Yeah, maybe. But a spontaneous reaction can also be really slow, right? The speed of reactions, that was covered in chapter 12 when we looked at kinetics. Here's an example of two reactions that are spontaneous but have very different speeds. If we look at the degradation or the radioactive decay of TC99M, so that stands for technetium 99 metastable. So basically it's a non-stable form of an isotope of technetium, which is a radioactive element. You see that over 7 days, it starts to, undergo that decay, okay, which is a reaction. It's a nuclear reaction. But if you look at this here, which is uranium-238, it's also a radioactive isotope. It also undergoes spontaneous radioactive decay, but you see that the decay must be really slow. After 7 days, it's virtually all there, okay? And that's true. The radioactive decay of uranium-238 is very, very slow. We're not going to get into how slow. We'll talk about that more in the chapter on nuclear chemistry. But again, don't mix up a spontaneous reaction with being a fast reaction. Now, I would be totally okay if you're like, I don't know anything about radioactive isotopes, Mr. Dion. Well, I bet you know about diamonds, right? All of my students have seen a diamond at some point in their life. Maybe you have a diamond earrings or a diamond ring or a diamond in your watch or something. Diamonds aren't that uncommon. Well, the formation of carbon as graphite, which is just a physical form of carbon, it's in fact the most stable form or allotrope of carbon. The formation of carbon, graphite, from diamond is actually a spontaneous process. Yeah. And I think I've brought this up in class. In fact, I'm pretty sure I mentioned it in the kinetics chapter. So again, an allotrope is just a different physical form of an element. And carbon has two allotropes here, diamond or graphite. But the conversion of diamond to graphite is a spontaneous process at ambient pressure, okay? And but it says here that its rate is immeasurably slow at low to moderate temperature. So you can speed it up by cranking up the temperature, but you're probably not going to subject your diamonds to high heat at any point in time. So again, this is a spontaneous process. Your diamonds are slowly being converted into dust, but it's so slow that you don't have to worry about it at all. Okay, so don't mix up spontaneous and fast. Just because it's spontaneous doesn't mean it's a fast reaction. Some spontaneous reactions are super fast. Other ones might be super slow, like these two examples here. Give me a thumbs up if you follow me on this so far, just where we are so far, just what a spontaneous reaction is. Cha, is everybody with me on that? Not meant to be blowing your minds or anything, just kind of getting into the content here a little bit. Great. Well, let's keep going on our conversation regarding spontaneity, or what's a spontaneous reaction. Well, it says here that if you have a spontaneous reaction in one direction, it's going to be non-spontaneous in the reverse direction. Now, I'm sure that some of you figured that out already, but that is, by definition, if the reaction is spontaneous in one direction, it's going to be non-spontaneous in the reverse direction. Now, if we take a look at this example here, if you take hydrogen and you burn hydrogen in the presence of oxygen, that's a spontaneous reaction. That's what's going on right here. Okay, this is the best picture I could find. I don't even know if you can make out what's going on here, but there's some hydrogen in a balloon, and then there's some oxygen in the air. Then there's a candle, and some fool gets the candle too close to the balloon, or maybe the scientists did it on purpose, and they end up combining the hydrogen and the oxygen, and they make some water. But there's something kind of missing from this picture, isn't there? right? It's not really showing you the truth, because that's also going to form what? A lot of heat. Okay, and if anybody here has ever ignited hydrogen before, you know that that's an exothermic reaction. It's going to release a lot of heat. But what you probably haven't seen done before, or I'm sure somebody that's hearing the sound of my voice has tried this, is if you take water, you can do the reverse of this reaction right here, right? You can reverse that spontaneous process. It's a non-spontaneous process. How would you do it? Well, you continually put energy in, right? You can even see that this is an ever-ready battery, right? This is the energy. So if you put energy into water, so this is just water. Let me use a better marker here that you can see. This is water down here. And this process is called electrolysis. When you pass a current through the water, so that means you're going to have energy plus the water, you produce hydrogen and oxygen. So this would be the hydrogen over here, because there's twice as much of it as there is the oxygen over there. So heat is a form of energy. Okay, so there we go. So we can take that spontaneous process and we can reverse it. However, it's going to require a continual input of energy. And if you're the kind of student who likes to look up everything, you know, this process again is called electrolysis. Has anybody tried this before in high school or anything? There were two guys that I went to high school with who were obsessed with electrolysis and trying to capture hydrogen gas. Has anybody ever tried this before? No, sir. Okay. Yeah, I went to school with two guys who were just obsessed with trying to generate or collect hydrogen, but it's not easy to do. You know, they were trying to find a way to separate it and then just a way to collect it over the water like this. It wasn't simple, but I remember that they ended up collecting some hydrogen in a balloon. They worked really hard at it over a weekend, and these were good students too. And they told they were hanging out together, and they told one of the guy's fathers, were like, "Hey man, we get some hydrogen in a balloon. Do you mind if we ignite it?" And he said, "No, as long as you do it in the driveway." So anyhow, these two guys, all dressed up in their what safety gear they had. They were just high school students, and they went and they lit the balloon out in the driveway. So anyhow, all right. You're probably wondering what happened. Well, it didn't look like this, okay? It didn't look exactly like this right here. Do you guys know what's going on in this picture that I have down here at the bottom? Does anybody recognize that?
The Hindenburg disaster.
Yeah, it's the Hindenburg disaster that occurred in Lakehurst, New Jersey in the 1930s. So the Hindenburg was a Zeppelin or an airship that was came from Germany, and it was filled with hydrogen. So this thing is filled with hydrogen, and then there was a spark, I guess, or somebody. I don't know. My students probably know what started the fire. It wasn't Billy Joel. I think it was probably a cigarette or something like that. Yeah, somebody says they were trying to land it. I'm not an expert, but I know that there was hydrogen gas in here, and I know that there was oxygen over here, and I know that somebody added a spark to it, and that it released they produced some water vapor, but that's not what's of interest. They also produced a lot of energy, right? Plus a lot of heat. Let's capitalize on it, right? Plus it generated a lot of thermal energy. So it says here, many spontaneous processes proceed with a decrease in energy. So this is an exothermic reaction. That's what you could say here. So you could say exothermic, right? It's releasing heat energy. Recall that exothermic reactions also proceed with a decrease in energy. So I'm repeating myself here. But here's something that is not intuitive. And this is where we're kind of stepping up, moving up a step in the complexity of what we're talking about today. Is that spontaneous reactions? Yeah, a lot of the time they are exothermic. Okay, and you spent a lot of time studying delta H, right? You remember enthalpy, H, right? So when delta H is negative, that's an exothermic reaction. That would be something that you would have learned in the thermochemistry chapter, which was covered in chemistry 1401. So again, you looked at a lot of exothermic reactions, and oftentimes those are spontaneous, but not all the time. Okay, it's not 100% guaranteed that just because a reaction is spontaneous or reaction is exothermic, that it is spontaneous. If you were a betting person and you said, well, I could bet that most of the time they will be, you'd be right, but not always. So if you're wondering, can you give me an example of an exception, Mr. Dion? Yeah, I can give you an example of a very simple exception. Melting an ice cube, okay? If you're at McDonald's and you get a piece of ice, in your drink, right? McDonald's is notorious for giving you 10% liquid and 90% solid. They love to give you lots of ice. Anyhow, well, when water in the solid phase, so when ice, okay, so when ice is converted into liquid water, you see that the delta H is positive 6.01 kilojoules per mole. That means that this is an endothermic reaction. Endothermic reaction, right? When delta H is positive, it's endothermic. If we look at what's going on down here, we're taking water, and we're freezing it. So we're taking water and we're converting it into ice. This is exothermic. Okay, which one of these reactions occurs spontaneously at room temperature? The conversion of ice to water is the one that is going to occur spontaneously at room temperature and with a pressure of 1 atmosphere. And so endothermic, but might be endothermic, but it's spontaneous. Okay, and this reaction, the second one, or this physical process, is not a reaction, but this process of water being converted into ice, that's exothermic, but it's non-spontaneous. And non-spontaneous isn't hyphenated. I know I had it hyphenated on a previous slide, but it's not hyphenated. So there you go. So we back up. Yes, most exothermic reactions are going to be spontaneous, but not always. And here's a beautiful example here of the physical process of ice being converted into water, right? The ice is going to absorb heat from the environment. So this is an endothermic reaction. But heck yeah, we know it's a spontaneous process. There we go. Well, let's talk about the dispersal of matter. So it might seem that we're switching gears here a little bit, and we are to a certain extent, but it's going to come together come together with respect to our discussion on spontaneity. Okay, so let's say we have a bunch of particles on the side of this bulb system here. So these are just two bulbs that are attached by this stopcock here. So that's just, it's kind of a valve that's going to close it off like that. And you know what? If you guys are the kind of people who like to maybe look at a different chemistry textbook besides the OpenStax textbook, I like to sometimes bolster my lectures by looking at the CHEM textbook, which is a textbook I taught from for a number of years. But I looked at that textbook, and I looked at an old textbook, which is called Ebbing, which I wouldn't expect you to ever find. But all three of those textbooks had some iteration of this figure. So this figure is basically ubiquitous in general chemistry as a way to explain the dispersal of matter and how it relates to spontaneity. So we have a bunch of particles on this side over here, and over here we have a vacuum. Okay, so there's nothing on the other side. And if we open up that stopcock, all right, if we open up that stopcock, you're going to see that spontaneously the particles are going to spread out throughout the entire vessel, right? We have an even dispersal, or they're just evenly spread out through both sides of this, container. So the gas spontaneously expands to fill both of those containers. Now, something that might not be as intuitive is that we're going to assume that the walls of the container are insulated to some degree. And so when we have an ideal gas, that this is spontaneously going to happen. And we know that there's no change in energy, right? If there's no exchange of heat with the environment, then there's no change in energy. Well, if I want to calculate the overall change in energy for this process, okay, which is delta U. So delta U stands for change in energy. And this, again, is a formula that you would have seen in the thermochemistry chapter of Chemistry 1401. You remember that change in energy is equal to heat plus work. Well, how much work is being done when I open up this stopcock? If this is a vacuum, that means that the pressure in here is equal to 0. Work, you might remember from the thermochemistry chapter, is equal to the negative of P times the change in volume. Well, if my P is 0, that means that the work is 0. And if there's no heat exchanged between the system and the surroundings, that means that my Q is going to be 0. And that's what I was getting at, was this bullet point here when I was tracing the outside here, okay? Well, based on the first law of thermodynamics, the change in energy is equal to the heat plus work. If both of these are zero, that means there's no change in energy. Now, if you're like, oh, okay, cool, yeah, great, man, no change in energy, big whoop-de-doo. Well, hold on. Then if there's no change in energy, what the hell is the driving force? Pardon my language, but what is the driving force between this happening? Now, I'm sure it's intuitive to most of you to just be like, well, come on, if you open it up, they're going to spread out. You know, it's going to balance out the pressure. It's going to, well, we just said it's got nothing to do with the first law of thermodynamics. Okay, there's no change in energy, so there has to be some driving force. And if you really want me to get ahead here and kind of reveal what the answer is, you know, pay no attention to the man behind the door, right? If you want me to tell you what the answer is that the driving force is entropy, right? That's where we're going with this. But I'm trying to unfold the story in front of you and kind of, you know, break it down bit by bit. So to summarize, it says that the spontaneity of this process, as we just discussed on the last slide, is not a consequence. So not a consequence of any change in energy. It's got nothing to do with delta U. Instead, what's pushing this forward? Why is it that when we open the stopcock that the particles spread out? It's got to do with what? It's got to do with this. This is put really eloquently: a greater, more uniform dispersal of matter. Okay, so that greater, more uniform dispersal of matter is going to be what's causing this spontaneous process to occur. Okay, so let's talk a little bit more about this greater, more uniform dispersal of matter. Right, that's what we're going to be concerned with. Well, so far we've looked at matter. What about energy? Well, let's take a look at energy. So now we're going to switch gears slightly here and talk about not dispersal of matter, but dispersal of energy. And as I told you earlier on, if we have two objects and we put them in contact, if one of them is hot and one of them is cold, spontaneously the heat is going to flow from the hot object to the cold object. But overall, and this might not be intuitive, there's no change in energy in this process. What? There's no change? No, there's no change in energy. Now, why would that be? Well, if we take a look at the temperature of the hot body, which we're going to assume is X, and the cold body, which is Y, right? Hot is always represented by red and cold is always represented by green. Well, we see that the heat of X is less than 0, right? What does that mean? That means that the X is going to lose heat, right? Because when Q is negative, that means that the body is going to be losing heat. So you could say X loses heat. We'll say it like that, okay? Well, whatever X is losing in heat, right, that means that Q is good, Y is going to gain it. So whatever heat is lost by X is gained by Y. So we could write that out. Heat lost by X is gained by Y. So we didn't destroy the energy, right? You can't destroy energy. So what happened? That thermal energy wasn't lost, right? It says here there's no net gain or loss of thermal energy. What happened? It was redistributed. What does that sound like? Sounds a lot to me like uniform dispersal, doesn't it? Right? It's kind of tying the two things together. Okay? The spontaneous process resulted in a what? A more uniform dispersal of energy, right? The last slide we looked at a more uniform dispersal of matter. Now we're talking about a more uniform dispersal of energy. Okay, there we go. So if we look at both of these processes, whether we're dealing with matter or energy, we see the same idea coming up. Okay, that why are both of these processes spontaneous? Why do these particles spontaneously spread out into the container when I open up the stopcock? Why does the heat flow from the hot body to the cold body? Because the spontaneous process took place and it resulted in a more uniform distribution of something, whether it's matter or energy. So that more uniform dispersal is what's pushing this forward. Now you're probably, again, I'm sure that a lot of you are connecting the dots and saying, well, when it's more uniformly spread out, that means that there's more ways that I can arrange the particles. Therefore, it's going to have more entropy, right? There's more disorder. And you're absolutely correct, right? That's where we're going. So this is just kind of a rehashing of that same slide, rehashing of the last slide rather, but just to kind of add to it here, I put couple little bullet points at the end here, which is tying in what we said in the last slide. It says, it appears that greater, more uniform dispersal of matter and energy can also be the driving force. Okay, good. But the overall, or the major conclusion that we want to draw is this one right here. Is that if a process increases the disorder of the universe, it's going to occur spontaneously. Okay, that's going to be really important. That is going to tie into what's called the second law of thermodynamics. Now, if you're wondering about what is that factor, okay, that factor is what we call entropy. And that's why if you attended the synchronous lecture today, before I started recording this lecture, that's why my students and I had a little discussion about entropy and just about the word entropy. And we all kind of agreed that, or a lot of us agreed that the word entropy is just used to describe disorder, right? Somebody said, okay, well, if a messy desk, has a higher entropy than an ordered desk, or a messy kitchen has a higher entropy, right? It's just increasing the randomness or the disorder. And so again, and I'm rehashing the point here, but I want to make it abundantly clear that what's causing these spontaneous processes to occur is that there has to be a more uniform dispersal of matter or energy. That's what's driving the reaction forward, or the process forward. And if a process increases the disorder of the universe, it's going to occur spontaneously. We call that factor entropy, which is randomness or disorder. All right, there we go. Well, let's take a look at some examples here, or some problems. Some of the practice problems that I chose for this chapter came directly from the OpenStax textbook. I thought there's some really great problems in here, and I think this would be a good place to start problem solving as a group. So question number 3, you get a few parts here, A through F. It just says indicate whether the following processes are spontaneous or non-spontaneous. You're going to use your intuition, but I guarantee you my students are going to do a good job on a question like this. We already looked at the first 2 examples here. We said that if liquid, or sorry, no, we didn't look at the exact same questions as are in A and B. Let's go over them a little slower. So A says, if liquid freezes at a temperature below, which means lower than its freezing point, the freezing point of water is 0 degrees Celsius. So if water freezes at a temperature below its freezing point, would that be spontaneous or non-spontaneous? And again, there are no trick questions here. Excuse me. Could anybody tell me? Yeah. All right, that would be a spontaneous process, right? So this is, this would be spontaneous, right? Because the temperature is going to be less than 0 degrees Celsius. The next one says liquid water freezing at a temperature above its freezing point. Well, if you had water at, let's say, 10 degrees Celsius, why in the hell would it freeze? Pardon my language. Thanks, Joey. Sierra, you're both 100% correct. So that'd be non-spontaneous, right? Again, the temperature is greater than 0 degrees Celsius here. What's the next one? Combustion of gasoline. Notice that it says it's the combustion of gasoline. It's already burning. Is that a spontaneous process or a non-spontaneous process? Combustion of gasoline. Good. Yeah, I hope it's spontaneous. Otherwise, we're not going to get very far in our automobiles, are we? So this is spontaneous. So spontaneous reaction. The next one, a ball thrown into the air. Well, that's non-spontaneous. You got to put energy in to make a ball go up in the air. So non-spontaneous. A raindrop falling on your head, or a raindrop falling to the ground. What about that one? Yeah, absolutely. If the raindrop is falling, it's going to keep falling. It's not going to go up into the cloud. Yep, so that would be spontaneous. Spontaneous. And, I put up a picture of iron rusting, and we know that that's a spontaneous process. Spontaneous. It's one of the best things about living in Colorado. Of course, automobiles can rust here too, but not nearly to the extent they do on the coast. And you know that if you've lived on the coast, and I'm sure that many of you have lived on the coast at some point in your life. All right. Well, that covers section 16.1, dealing with spontaneity. And then kind of where we ended off was talking about entropy, right? That's kind of where we ended off. And that's where we're going to begin in section 16.2. The variable that we use for entropy in chemistry is the letter S. So entropy is represented by S, and something that we're going to talk about a lot in this class will be a change. So a change in entropy, which is probably not that much of a stretch for you, which will be delta S. But we're going to look at entropy and changes in entropy along the way. I'll just delete that. It's kind of messy writing. But anyhow, you've noticed this figure here is not the exact same as the figure that I put a few slides ago. That's because it came from a different textbook. Like I told you, the one that I had previously was figure 16.4, but this is the exact same as figure 16.4, which I told you, this is such a great example. That's why it's shown in every chemistry textbook, and I took this from a different textbook. Anyhow, so what is entropy? Well, we've kind of defined that as a class this morning. I got the help of my students to give me a good definition of entropy, which I have summarized here. It's considered to be a measure of the randomness or disorder in a system. Okay, so the randomness or disorder of a system is entropy. The more different ways that molecules can position themselves, the more disordered the system and the higher the entropy. So we have a greater entropy when we open that stopcock, right? We have an increase in entropy going from top to bottom. So I'll go like this. So entropy, so we'll say S increases, right? I mean, we could sit around here and discuss this for the next 5 minutes, but if you look at this definition, okay, and think about these particles here, it says the more different ways the molecules in the system can position themselves. Well, if I'm a molecule on this side of the ball or this side of the apparatus, when the stopcock is closed, I can only position myself in this side. As soon as that stopcock is open, there's more positions or there's more places where I can position myself. And so the disorder increases, okay? The particles are spread out in a greater space. And so the randomness or the disorder of these particles is increasing. Well, we tied in spontaneity with entropy in the last chapter, or the last section of this chapter. In spontaneity of a reaction is going to be favored by an increase in entropy. Okay, right? If spontaneous processes are favored when we have, or occur when we have a more random or a dispersal of matter or energy, well, spontaneity is going to be increased when I have a greater entropy, more randomness, a greater disorder. Okay, we see how these two are tied together. And Ludwig von Boltzmann, and I have a picture of his, that's his grave right there. So that's in Vienna. I don't know if anybody's visited it before, but anyhow, you can see there's an equation on his tombstone, which is S is equal to the K times the log of W. And I have something similar to that there. Now notice that they say that when it says log here, it's not a log, it's a natural logarithm. It's a log with the base of E, which is the same thing as a natural logarithm. And so that equation on his tombstone is represented right here. The entropy is equal to K times the ln of W. Now, if you're like, what's a K and what's the W? Well, K is a Boltzmann constant. We're not going to go into that. That's beyond the scope of our course. But the Boltzmann constant, if you need it in this class, I would, of course, provide that to you. It's 1.38 times 10 to the negative 23 joules per Kelvin. But W is the number of microstates. And you might be wondering, what the heck is a microstate? Well, a microstate is simply a specific configuration of locations and energies of the particles in a system. And the number of microstates is given by this formula here. Now, if you're like, I'm not sure what a microstate is. Well, the good news is I'm going to show you an example that covers what a microstate is. So again, a microstate is given by the letter W. So W is equal to lowercase n to the power of uppercase n. And we're only going to look at one example of that, of how to apply the whole concept of the number of microstates. So if we take a look at this slide here, I have the W, which is the number of microstates, is equal to n, the number of boxes, and then n would be the number of particles. So we have two boxes here, and then we have 4 different particles. Well, how many ways could I arrange those particles in those boxes. And you see that I have some scenarios where I have all the particles on one side of the box. I have scenarios where I have 3 on one side and 1 on the other. And then finally, I have a scenario where I have the particles spread out evenly throughout those 2 boxes. Now, each one of these, A, B, C, D, and E, we call these distributions. Okay, these are all called distributions. Maybe I'll write that down. So A, B, C, D, and E are called distributions. Well, if I look at those distributions, you can see that the most probable of all the types of distributions are the ones where the particles are spread evenly between the boxes, right? It's this one here. This is the most probable distribution of them all. It's where everything is spread out most evenly, right? Most disordered. Now I have that summarized right here, okay? So again, this is just showing you the definition of what the distributions are, which again are A, B, C, D, and E. The most probable one of the most probable configuration is one of the 6 microstates, this one here, where all the particles are spread out evenly between the 2 boxes. Now, you might be thinking, well, this is only 4 particles. What if I had 2 boxes, okay, but I had, a mole of particles, let's say 10 to the 23, okay, so if I have 10 to the 23, well, then you're going to get some kind of crazy number. But the whole idea is this, summarized in the last bullet point here. So no matter how many particles we have in our system, what you're always going to find is that the most probable configuration is going to be the one where you have roughly equal number of particles spread out in each box. So if we had an N, an uppercase N, okay, if we had that as being, if we had that as being 6.02 times 10 to the 23, then you get some kind of crazy number. It's a really big number if you had a mole of particles. But the idea is that then it's going to be even more probable, or the number of microstates where you have the particles spread out evenly is going to be even greater. Okay, that's the whole concept put together here. Okay. Now, what if we want to use this formula in a problem? Well, let me show you how you would do that, okay? First, if we look at the difference between initial and final entropy values. So let's say we wanted to calculate the change in entropy between 2 different scenarios where we have particles spread out between boxes. So we have our delta S, our change in entropy, is going to be equal to the final entropy, subtract the initial. So the Boltzmann constant doesn't change. So we could say the Boltzmann constant times the ln of the final number of microstates, subtract the Boltzmann constant times the ln of the initial number of microstates. So we shorten that to this, which is the delta S is equal to K, the Boltzmann constant, multiplied by the ln of WF over WI. Let's think about it. If, again, W is, oh, there it is right there. If W is the number of microstates and entropy is S, okay, if we have more microstates at the end, so greater disorder or greater randomness, okay, if we have more microstates at the end than we do initially, that means that this number is going to be greater than 1, and therefore we're going to have a delta S which is greater than 0. That means our entropy is increasing, right? So if we have more randomness or more disorder, entropy is decreasing or increasing. That makes total sense. The converse is also true. If I have less microstates or less randomness or less disorder or less of a even dispersal of my matter or energy than I do initially, then the number here is going to be less than 1. And I'm going to have a delta S, which is less than 0, right? The entropy of the system is going to decrease, okay? So if I, kind of try to tie all this together a little bit more, the most probable distribution, again, is going to be the one with the biggest number of microstates. Therefore, right, and this is a statement that I made already in class, so that means the most probable distribution is the one that has the greatest entropy based on this formula, right? Because S is going to be directly proportional to W. The higher the W, the greater the S. All right, there we go. So, you know, if I could explain entropy to somebody walking down the street, somebody who's not a chemistry student, I would kind of say to them, entropy is got nothing, is basically just probability, right? The greater probability is that, or the highest probability is that you're going to have the most disordered scenario, and therefore that's going to be the highest entropy. So highest entropy is going to be most probable. All right. Again, me kind of rehashing the same concepts here. The most probable distribution is going to be the one with the highest entropy. Okay, highest S is going to have the largest number of microstates. So highest W, which again ties into S is equal to the K times the ln of the number of microstates. And this is going to apply to all systems, even ones or especially ones where we have a larger number of particles, right? When we're going to be talking about chemistry, we're going to be dealing with huge numbers of particles, moles, right? There we go. So again, if we increase the number of microstates, we increase the entropy of our system. Now you might be wondering, how in the heck would I apply that to a problem? This is a problem that comes straight out of our textbook. It says calculate the change in entropy for the process that's depicted below. Now you might be looking at that and saying, well, that's not a chemical reaction, Mr. Dion. What the heck is that? Well, all that's being represented here is this is a microstate, right? And here we have one distribution. So that means that our initial number of microstates is 1. But if we look at the number of possible distributions over here, we have 1, 2, 3, 4, 5, 6. So that means that our final number of microstates is 6. So we go from an increase in entropy. So you're probably saying, well, my delta S better be a positive number because it's increasing, right? I'm increasing the randomness or disorder in this process. It's not a chemical reaction, but the same rationale applies. So how would we solve this? We'd use our formula that delta S, which is equal to the final entropy, subtract the initial entropy, is going to be equal to K times the ln of the final number of microstates over the initial number of microstates. So that means that delta S is going to be equal to the Boltzmann constant, which is 1.38 times 10 to the negative 23 joules per Kelvin multiplied by the ln of 6 over 1. So just the ln of 6. Take your calculator. Very quick calculation. Take 6, take the natural logarithm, you get 1.79 or 1.792. We can round off at the end. So it's going to be equal to 1.38 times 10 to the negative 23 joules per Kelvin times 1.792. Again, I'll round at the end, and we get that our delta S is equal to 2.47 times 10 to the negative 23 joules per Kelvin. Well, it might not have a lot of significance to you right now, this number, but the idea is this, is that this is a positive number, right? It's a positive number. So if the delta S is positive, so delta S is positive, okay, that means that entropy S is increasing. And if you're wondering, hey, if I ended up with a negative delta S, does that mean it's decreasing? Absolutely. Absolutely. Give me a thumbs up if you follow me on this one. If you think, hey, I think I could solve a problem like this. And I think there's a couple other examples in the problems, and I've chosen some problems from the textbook for you to take a look at. If you go on Canvas and look under the Chapter 16 module, you'll see I've hand selected some problems from the textbook. Of course, you have complete access to the solutions manual from OpenStax. It's free and available. You'll also see that I have a bunch of problems, of course, that I always put in the chapter, and we're going to try to take a look at most of those problems in class. All right, there we go. So entropy is also a state function. Things like, what are some other state functions that you've looked at in this class? Things, not in this class, but maybe in chemistry 1, things like volume, changes in volume, changes in enthalpy, energy, those are state functions. Well, since entropy is a state function, if you want to look at the difference in entropy between a final and initial state, we can say that the delta S, the change in entropy of our system, is going to be equal to the final entropy subtract the initial. Now, what kind of system are we interested in chemistry class? We're interested in a reaction. Okay, so that's what we're going to be looking at, most of the time in this class, is that the change in the change in entropy of a reaction is going to be equal to the entropy of the products minus the entropy of the reactants. And you might be wondering, hey, this kind of looks similar to, the formula that I learned for the change in enthalpy of a reaction, and you wouldn't be incorrect at drawing that conclusion. And I'm probably going to throw that equation in later on. Well, let's talk about things that change entropy. So now if you're, hopefully you're all with me at this point, but if you're kind of like, I'm not 100% sure about this entropy business, I bet you that when we finish looking at the next couple of slides, that it's going to really help your understanding of what entropy is. Okay, so if you're not 100% with us or with me so far, just take a deep breath and just see if you can follow with me on the next few slides, which will hopefully clear it up, especially this slide right here. Things that influence entropy. Remember, entropy is randomness or disorder. If I have a solid, right, a perfect crystalline solid that you see here on the far left inside this beaker, this Erlenmeyer flask with a stopper in it, well, that crystalline solid, you see the particles are all close together, right? They're not moving very much. Is there movement? Sure, there's absolutely movement. It's not an absolute zero, or I'm going to assume it's not an absolute zero. So there's movement there of the particles, but very little. So it shouldn't be that much of a stretch that when we go from a solid to a liquid, we have an increase in entropy, right? Are the particles still close together? Yeah, but there's a hell of a lot more movement, isn't there? Right now, the particles are free to move past one another when they flow in a liquid. And then hopefully it's even more intuitive that if I vaporize that liquid, if I convert that liquid to a gas, well, then the particles are going to be much further apart from one another, and they're going to be moving completely randomly. And so I get an increase in entropy there. Give me a thumbs up if you follow me on that concept, that as I go from a solid to a liquid to a gas, I'm going to get an increase in entropy as I go from that solid to a liquid to a gas. These phase changes. All right. Usually, they're not always, but usually my students don't struggle with this concept. Usually students are like, I'm on board, Mr. Dion. If I go from a solid, it's perfectly uniform, particles are all tight. Then I go to a liquid, particles are still close, but they're moving now. They have a lot more freedom of movement. Then I go to a gas, where the particles are much more spread out. That the disorder is increasing, or randomness is increasing. So the entropy is increasing going in this direction. Now, obviously, if you go in the opposite direction, if you take a gas and you condense it, then you're going to get a decrease in entropy. So your entropy is going to have a negative value. If you go from a liquid and you freeze it to a solid, well, then you're going to get a decrease in entropy. Okay, anyhow, so there you go. Phase of a substance. What else? Temperature of a substance is also going to affect its disorder. Right? Think about temperature. Temperature is directly related to the average kinetic energy of particles. So as the temperature increases, particles are going to move faster, right? Greater freedom to move, they're going to be moving faster. And so the effect of temperature on entropy is shown right here, right? If I look at the relative amount of kinetic energy of particles, as I increase the temperature of the particles, you see that the average kinetic energy, and we're not going to talk about the Boltzmann distribution today, but the average amount of kinetic energy increases. So more kinetic energy, more freedom to move, more random. Now, what else with respect to this effect of temperature on entropy? If you had to look at it from the point of view of phase changes, it says that the effective temperature on entropy is due mostly to phase changes. So let me show you what this statement here means, okay? Oops, it was supposed to be a highlighter. If you're not 100% sure what that means, look at this graph right here. Here I have entropy on the y-axis and temperature on the x-axis. So follow with me. I'm going to use my, let's see what I'll use. Maybe the green highlighter will work. So if I start down here, I get a solid at 0 Kelvin, so it's an absolute zero. It's going to have no entropy whatsoever. And if you're like, isn't that tied to the third law of thermodynamics? Yes, we'll talk about that in a bit. Well, what's going to happen is I increase the temperature of that cell, the particles are going to start vibrating more and more and more and more and more and more. They're going to start moving faster and faster and faster. It's still a solid. Like, are they moving a little bit more? Yeah, just a little bit more. And then I get to a phase change where melting occurs, right? That's what's happening on this line right here. This is melting. I mean, you could say melting or freezing, but we'll say it's melting because we're looking at the increase in temperature, right? So it says melting right here. That's what that line is. So what happens as I melt the substance, right? The temperature doesn't increase during a phase change because all the energy that's being put in is going into converting the solid to a liquid. So the temperature doesn't change during melting. Okay, that's something that we would have covered in chemistry 1401, but look what happens to the entropy. It goes up a ton, right? Because at the beginning of melting, you've got mostly solid, but at the end, you've got mostly liquid. So that makes sense. The entropy is going to increase drastically. Then what happens? You take that liquid, right? The entropy is increased. You start warming it up, warming. The entropy is, right? The particles are moving faster and faster and faster as you heat it. Then all of a sudden it gets to a transition between liquid and gas, right? This is boiling or vaporization. Now look what happens. The temperature doesn't change as it gets converted from a liquid to a gas, but look what happens to the entropy. It goes up a ton. Okay? And so that's what's going on here. And of course, when you make a gas, you can heat it higher and higher and higher, and the particles are going to move faster and faster and faster. Their entropy is going to increase. But what it's saying here is that the effect of temperature, right, is mostly going to be due to these phase changes here. Okay, that's where most of the increase in entropy is going to come from, is from the change in phase. All right, there we go. Next one. Now, the first two I think are pretty intuitive to my students. Usually they're like, yeah, of course, if you crank up the heat, the particles are going to move faster. It's going to be more disordered. If you go from a solid to a liquid to a gas, yeah, particles are going to become more disordered. It's a positive change. It's an increase in entropy. Well, the third and fourth one might not be as abundantly clear, but they are usually when my students see it. So the third one is the type and number of particles that make up a substance. So the more particles that we have, okay, and the heavier the particles are, so we'll put here greater number of particles and greater mass equals increase in entropy. All right, so greater number of particles and greater mass means you're going to have an increase in entropy. Let's say, for example, you were to compare, let's say, butane with ethane. Now, if you don't know what butane and ethane are, I'll help you out. If you look at butane, it's got a molecular formula with just C4H10. That's butane, like in a butane lighter. And if you look at ethane, it's C2H6. Well, they both have the same types of particles, right? They both are made of carbon and hydrogen. But the thing is that I have more particles in butane, right? And overall, it's got a heavier mass. And so since it's got more particles, the butane is going to have a greater S, okay? Greater entropy. Well, with that in mind, let's take a look at some problems. Now, I thought this would be the best way to clear up this bullet point, number 3, would be by taking a look at a problem. Now, you can see how this would lend itself to a multiple choice problem so easily. It says here, arrange the following sets of systems in order of increasing entropy. Assume 1 mole of each substance and the same temperature for everything. Okay, so we've got hydrogen perbromic, HBrO4, so that's HBrO4. Then we have hydrogen bromide. Which one of these is going to have the greatest disorder? Can anybody tell me which one of these would have the highest entropy? H2, HBrO4, or HBr? Yeah, HBrO4 is hydrogen perbromate. I started to say hydrobromic acid, but it's in the gaseous phase. So yeah, HBrO4 is going to have the greatest entropy. H2 is going to have the lowest entropy, and HBr is going to be somewhere in the middle. And the reason why that they're in this order is because it's due to increasing mass and complexity of molecules. Okay, what about the next one? Can anybody tell me, out of helium, chlorine gas, and P4 gas, which one of these would have the least entropy? Which one would be the most ordered? Lowest entropy out of these three, and it's not a trick. Yeah, thanks, Joel. Thanks, Sierra. Yeah, helium is the second element on the periodic table. It's really light, and there's only one particle in it, right? Chlorine has got 2 particles in it, and the P4 has got 4 particles, right? So the mass is increasing as I go from helium to Cl2 to P4, and so they're actually listed in the correct order. But we'll write it like this, that we go from helium to the Cl2 and the P4, and of course these are all gases. I should have included that, but whatever. And we get the same rationale, that the entropy is increasing. I'm just going to copy this and paste it over here. So paste. And it's not, these aren't all molecules. So we'll say it's increasing due to increasing mass and complexity of species, because helium is not a molecule. All right, there we go. So that's the next one. By the way, last night I looked over one of my colleagues' old exams, where on chapter 16, or some questions, and he had a question very similar to these ones here. So I'll probably put a question very similar to this on your practice exam and your next exam. And then the next one, and this is the last one, I promise. So the first one was states of matter. The second one was temperature. The third one is number and types of particles that make up the substance. And the fourth one is pure substance versus a mixture. Okay, the variations in the types of particles. Now this one, again, I think is usually pretty intuitive to my students. You know, which one is going to have a higher entropy? If I have just some Kool-Aid crystals that are a solid, right? Or if I have Kool-Aid where the particles are going to be spread out in water. Which one do you think is going to have a higher entropy? Kool-Aid crystals or Kool-Aid, the drink? Anybody have a feeling about that? The drink. All right. Yes. You're absolutely, you're all 100% correct. Yes. So we'll put here higher entropy, right? Right. Because when you have just the pure crystals, right, they're all locked together in that crystal lattice in that cell. There's very little movement of the particles. When you put them in the drink, I mean, come on, they're spread out. They're in the water, right? They're solubilized. They'll put my description down here is a lot sassier than what I just say. It says the particles compared to the pure substance in which all particles are identical, the entropy of the mixture where you have the water and the Kool-Aid crystals is going to have an increase in entropy, right? There's a more uniform or a more random dispersal of the particles. There we go. I told you that you guys would find that one intuitive. I just looked at your answers. Like sometimes I'll scroll back and look, what did my students say? And you all get it right. Okay, so usually I'd say that the first point I'd say is students always nail this one. Second one, increase in temperature, increase in thermal energy, particles move faster. Yeah, students usually nail that one. Third one usually takes a little bit of just me kind of explaining to you the concept. And the whole thing about mass, the whole thing about greater mass of a particle is really beyond the scope of our text. He mentioned, or the author mentions it very briefly, but you just have to kind of take my word for that one. And you can look at the rationale as to why. I won't ask you about it, but it is mentioned like super briefly, maybe one sentence about it. And then usually number 4, my students usually just blow this one out of the water. No pun intended. They usually just nail this one. Okay, students are usually very good at this concept here. So with that in mind, I want us to take a look at another question. Kind of flipping around my notes here, and again, you can see that this would lend itself to a multiple choice question really easily. This is one of my problems that I posted in here. So if it doesn't say it's from OpenStax, that means it's one of Mr. Dion's problems. And I have the solutions to these problems posted on Canvas. If you look in the chapter 16 module, it'll say something like chapter 16 slide solutions or something like that. I don't know. And I'll have the answers for these ones in here. But let's see if we can get through this one pretty quickly, because I want to move on to the next section with you guys and talk about the second law of thermodynamics before we end today. Not to be fast, but just I'd like to introduce the concept to you. And just give me 1 second here. Where are you guys? There we go. Okay. The following processes indicate whether the entropy of the system increases or decreases. So first one, vaporization of a liquid. That means we're going from a liquid to a gas. What's going to happen? S increases or decreases? Yeah, thanks, Katie. Yeah, absolutely. So increases, 100% correct. The next one is freezing of a liquid. So that means I'm going from a liquid to a solid. Yes, again, my students are really on the ball. Decreases. Oh, this is a good one. An increase in the number of moles of products versus reactants. Anybody have a feeling with this one? See? Yeah, good. It's going to be an increase, right? If I'm increasing the number of moles, that means that the number of microstates is increasing, right? You're going to have more microstates. If I have more moles, right, I'm going to have more ways to arrange the particles. And since delta S is equal to K times the ln of WF over WI, if WF is greater than WI, I have a number greater than 1. Therefore, my delta S is going to be positive. And therefore, the entropy is going to be increasing. So increases. What if I cool a block of ice? Okay, if I take a block of ice that's solid and then I cool it down even more. Yeah, thanks, Sierra. It's decrease. Now there might be somebody saying, well, come on, it's still a solid. It's just a solid, but hold on. The particles are going to have more movement at -10 than they will at -20, right? I'm cooling it, therefore I'm removing, or the thermal energy will be decreased for those particles. So they're moving less. And so the entropy is decreasing. And then finally, what if I compress a gas? What if I take a gas and I compress it? Yeah, for E, it's going to be decrease as well. Decrease. All right, think about it. If I have some gas particles in a environment, so let's say 1, 2, 3, 4, 5, 6, 7 particles like that. If I take that same container and I compress it, now I've got 1, 2, 3, 4, 5, 6, 7, right? So the number of microstates, right? There's going to be less disorder, right? As I go from here to here, there's less room for them to spread out. And so we could say here less freedom of movement for the particles. All right, again, you can see how this kind of question would lend itself to a multiple choice question for your next exam really easily. Is it already 10:35? Jeepers. Okay, well, give me a thumbs up if you're feeling good about this chapter, first 2 sections. If you're like, you know what, I think I'm understanding this. Yeah, cool. Awesome. That's great. That makes me really happy. You guys, it seems like a lot of students are following along. That's fantastic. Well, that brings us to section 16.3, which deals with the second and third laws of thermodynamics. I've already referred to both of them, haven't I? I'm kind of getting ahead of myself. Well, I don't want to go too fast, but we got 5 minutes left. I just want to cover a couple ideas, and then we'll revisit these ideas on during our next class. So you heard me talking about the system a bunch of times, And I told you a few slides ago that the system that we're interested, it says here, the system is the part of the universe that is of specific interest. Well, the system in chemistry class, as you can probably guess, the system is going to be the reaction that we're going to be investigating. So system just means a reaction in chemistry class. You can see here's my reaction in an Erlenmeyer flask. It says the surroundings constitute the rest of the universe outside the system. Well, you know what? If I do a reaction in the lab, let's say I, mix sulfuric acid and sodium hydroxide, it's going to make some heat. Okay, it's an exothermic reaction. But is that heat really going to affect what's happening out by Pluto? Like millions of miles away, at the outer reaches of the universe? No, and we can't get there anyway. And so the surroundings are actually the entire universe, but of course, we're only really interested in the immediate surroundings, okay, surrounding our reaction. So that's the surroundings. Surroundings are the environment close to the reaction. And then if we put the whole system and surroundings together, we call that the universe. And you're like, that's not the universe, Mr. Dion. The universe is bigger than that. Well, I know it is, but in chemistry class, that's what we call the universe. So you're going to, and if you're like, why do I need to know this? Because you're going to hear me talk about system, which means the reaction. You're going to hear me talk about surroundings, which means the environment next to the system or the reaction. And you're going to hear me talk about the universe, which is just the system and the surroundings. Well, what the heck does system, surroundings, and universe have to do with entropy and disorder and randomness and spontaneity? Well, it's summarized in the second law of thermodynamics, which is this right here. First of all, and the second law is down here, but first of all, the entropy change of the universe is going to be the sum of the entropy changes for the system and surroundings. Okay, great. So that means if you tally up the change in entropy for the reaction and the change in entropy for the environment around the reaction, that equals the change in entropy for the entire universe. Well, here's the second law. And this is kind of what I wanted to show you before we end the lecture today. Is the second law of thermodynamics is nothing more than this. If you want to have a spontaneous reaction, right, going back to section 16.1, it's got to cause an increase in entropy, section 16.2 of the universe, right? So we spent all of 16.1 talking about this. We spent all of 16.2 talking about this. And now we're tying it together in 16.3 and saying that in order for us to have a spontaneous process, nothing more than this. The change in entropy of the universe has to be positive, right? In order for a spontaneous process to occur, you've got to have an increase in disorder in the universe. So that's kind of a nice place to stop for this lecture. It's a really nice place to stop. And next class, we're going to tie in this whole idea of a spontaneous process is one where the change of the entropy of the universe is increasing. And we're going to take a look at it from the point of view of the system and the surroundings. You can see that my next slide even talks about the system. And then, of course, after that, we'll get into the surroundings. So the next class is going to be a little more complex than what we looked at today. But if you understood what was going on in today's lecture, that is going to be a very good foundation to build on for the remainder of this chapter.